Hi NASA, my name is Matt. I'm on the CS team for the RoboUtes this year. I'm going to talk about the communications diagram we've got here for Col 7, which is the 7th iteration of the cellular operated land explorer. Got the acronym. Alright, so there's three major steps. So you'll see on the legend we have Iris, Hermes, and Hydra. I'm going to go through them starting from mission control to the lowest level systems of the robot, so things that actually interface with motors and whatnot on the robot. Alright, so system number one is Iris. So this is an improved version of the in-house library that we wrote last year. So it communicates over TCP/IP, so it goes all the way from the terminals in mission control up over T-Mobile's 4G LTE network onto the Cradlepoint modem and into the NUC, the onboard computer on the robot. So it sends things over in key value pairs, which is extremely convenient for rapid development because it makes it so basically as long as the people on either side have any remote idea what the data is going to be, they can really quickly iterate and make changes on both sides, like add new commands and features and whatnot. So that the flexibility is really nice there. It also monitors the state of the connection and tries to self-repair, so if there's any connectivity issues, it'll attempt to reconnect. It tells both sides the status of the connection, so the robot could stop if it decides it's been disconnected for too long. It shouldn't just keep driving in a straight line. Also, the controllers in mission control can recognize immediately when there's a connection problem and try to remedy it as fast as possible. Alright, so stage 2 is once the data is on the NUC from Iris. Also, all of these are two-way, so it's important to know the NUC can send things back to mission control, obviously. So once the data is on the NUC, it has to get onto the low-level embedded hardware on the robot, which in this example, which is actually our diagram, are the ARM and Drive BOSS microcontrollers. So Hermes is a serial protocol, so they are plugged in to the NUC via USB, and they just use CDC, so just high-speed USB transport, and it is also a key value pair system. So if the data sent to the NUC from mission control is destined for systems beyond the NUC, you can just pass it right along from Iris to Hermes. They're directly compatible, which is really nice. That's another way in which it's easy to add features at any point in the robot and have people all the way back in mission control change their implementation really quick. So once we get it into like the C++ embedded hardware world, everything becomes wireless, which is nice because we have way less wires. We don't have a bunch of SPI and I2C running all over the robot. We just have power, which is still a bunch of wires running all over the robot, but that's okay. So once it's wireless, it runs on a system called Hydra. So Hydra operates on 2.4 gigahertz. It is not key value pairs because it's directed. So when I say directed, I mean the ARM BOSS does not just broadcast to all of its clients. It broadcasts to one client at a time. And that client has an ACK, so that it has an acknowledgement when it receives a message. So it's secure transport directly to specified clients. So all of those connections are monitored, the Hermes connection is monitored, and the Iris connections are monitored. So if anything anywhere in this chain goes wrong, people on both ends, well, robot on one end, people in mission control are made aware of that and can adjust accordingly.
The RoboUtes have been quite pleased with the compliant spine articulation system and have again implemented it in this year's rover. The passive spine allows all wheels to keep contact with the ground even while traversing very difficult terrain. The slip steer configuration seen here operates well on most surfaces, including all those found at the Planetary Analog Test Site at the Johnson Space Center. It is a very simple design, limiting the points of failure while maintaining excellent controllability. In designing the previous rover, the RoboUtes developed the innovative field-replaceable mobility module in order to simplify drive system troubleshooting, increase robot uptime, and provide a contingency plan should a motor or controller fail during the competition. This year, the team has redesigned the firm from the ground up, creating a much more robust system in the process. In designing the new manipulator, much attention was given to the shoulder joint. In the previous rover, this joint was not sufficiently supported and was somewhat underpowered, causing oscillations to travel the length of the arm. The arm seen here demonstrates some improvement in that area due to the rigid box tube humerus. The new shoulder will incorporate a friction clutch to protect the motor should the arm become stalled against an obstacle, but has yet to be constructed as it is awaiting the arrival of the primary motor. This motor is scheduled to arrive during the week of February 14th, at which point arm construction will begin in earnest. In the meantime, this development arm is being used by the computer science team to test their communication systems.